Welcome to Lecture 3 of an Introduction to Inductive Logic. In this lecture, we dive into our main inductive logic, probability theory, learn its axioms, explore some of its key definitions and basic propositions. To recap, we previously looked at the distinctive properties of deductive and inductive arguments, where what we found in the deductive case were clear and well-defined notions that we could grasp of the strength of inference from the premises to the conclusion, characterized by validity, producing an attitude of full belief when the premises were also true, that the proposition involved in the conclusion was either true or false, whereas things were somewhat less clear in the inductive case, where we found that the relationship of inference between the premises and the evidential support that they provided for the conclusion was characterized by something like inductive strength that let us arrive at an attitude of something like degrees of belief or confidence in the truth or the likely truth of the conclusion. The task of any inductive logic, then, is to get more clear on these notions of the inductive strength of inference and of the degrees of belief we apply or should apply to propositions. The most flexible and robust inductive logic we have for assessing both inductive strength and degrees of belief is provided by modern probability theory. We will look more at the justifications for this claim and other interpretations of probability in later lectures. For now, we have the following aims. By the end of this lecture, you should be able to 1. State the axioms of probability theory, 2. Interpret propositions in terms of Venn diagrams, 3. State the definitions of mutual exclusivity of events or propositions, of probabilistic independence, and of conditional probability. And 4. To use some propositions of probability theory to solve basic problems. In the previous lecture, we familiarized ourselves or refamiliarized ourselves with some basic portions of propositional logic. Moving forward, it will be helpful to recognize an equivalence between those parts of propositional logic with which we're familiar and some of the vocabulary of set theory that we'll be using in probability. In particular, we'll want to know that a proposition, like the coin came up heads, is going to be equivalent to the same event that the coin came up heads, and that a tautology, right, think P or not P, is equivalent to the sample space, where the sample space is any event occurring, the event that P occurs or the event that not P occurs. Similarly, a contradiction will be equivalent to the empty set. For the contradiction, think P and not P. And for the empty set, you can think of it as the event that nothing occurs. Similarly, for the logical connectives with which we are familiar, they will map on to set theoretic operations, that is, operations on sets or events. In particular, disjunction or will map onto the operation of union, in which we take the union or the combination of two sets interpreted as events. Conjunction and will map on to intersection, where we look at the intersection of two sets or events. And negation not will map on to set complement, where we look at everything that is essentially not in a set or event. elegant relationship is justified via Stone's representation theorem, which we will not go into here. Now, it will be helpful for us to pick up another method of visualizing and reasoning about propositions and now events or sets. And we can add this to our body of methods, including truth tables. I want you to imagine first a background set of all possibilities. This is denoted by the symbol omega for the sample set. You can imagine that this is all ways that a die could come up, 1 through 6, all ways that a coin could come up, heads or tails, all ways that an election could turn out, or all of the average heights that could be produced by a sample in a statistical context. Then a proposition, say P, picks out a set of those outcomes or events. And another proposition Q picks out another set of those outcomes and events. Now we can see that we can apply our basic logical operations in this context. So the portion of P that is outside of the overlap with Q will be P and not Q. Similarly, the portion of Q that is outside of its overlap with P will be not P and Q. And their intersection will correspond to P and Q. And the space outside of either circle will correspond to not P and not Q. Further, we can think of applying disjunction to characterize the same space so that the union of the two events P and Q will be given by P or Q. And that same space outside of either of them can equivalently be described as not P or Q. Here, recall that the sample space, the event that anything at all happens, is going to be equivalent to the tautology, which is going to be equivalent to propositions like P or not P. And you can take a moment to visualize what P or not P might look like. Propositions like Q or not Q, or P or Q or not P or Q, or P and Q or not P and Q. And the empty set, the null event, is equivalent to the contradiction, so that we have other equivalent propositions like P and not P, and Q and not Q, and P or Q and not P or Q, and so on. And a helpful fact will be that whereas the entire space is given by the sample set corresponding to the tautology, the empty set gives the contradiction, is a kind of, null event, the non-event, and is technically always a part of every set. So with that in hand, let's move on to the origins of probability, which by some accounts are located in the 17th century and in what are known as the Pascal-Fermat correspondence, which began when a professional gambler, the Chevalier de Mer, approached the famous mathematician Blaise Pascal to help him with certain peculiar problems in games of chance at the gambling table, who then approached Pierre de Fermat in helping him to think through these problems. And from the correspondence of Pascal and Fermat, we have some of the first rigorous treatments of probability. However, the modern foundations of probability are given by the Kolmogorov Axioms. That is, this is their most developed and mature form. These axioms, or foundational assumptions, produced by Komograph in 1933, are the basis of our extraordinarily successful, indeed our most successful, inductive logic. And they remain central and direct effort in mathematics, computer science, and elsewhere. Indeed, everywhere we have to deal with uncertainty. For a brief potted history, it's nice to observe that Kolmogorov made enormous contributions to modern thought. His seminal text on the subject of probability is given in the Foundations of the Theory of Probability in 1956, but he also made extraordinary contributions to our understanding of both randomness and complexity, which is captured in his work on tables of random numbers, published in 1963. And he has a very interesting story in which, during Soviet-era Russia, he protected a large group of other mathematicians who would otherwise be persecuted by the government, and managed to produce an enclave of people living and able to produce extraordinary work in spite of the rather dire and oppressive environment they found themselves. The basic setup to understand probabilistic thinking is that of a measure space. And this simple mathematical object is going to represent our beliefs about a given learning situation. So you can think of us reasoning about coin flips, or rolls of a die, or outcomes of cards, which are the conventional objects of games of chance that probability is typically taught in, because primarily of the simplicity of those contexts. But indeed, the learning situation is just as easily and well one of reasoning about the outcomes of elections, of medical outcomes, from different treatments to the truth or falsity of scientific theories and findings. So the first object in our measure space is the sample space, which we have already become acquainted with. The sample space is a set representing the possible atomic propositions under consideration. Here, for example, we think of the outcomes of a single coin flip, the single toss of a coin, heads or tails. The second object is the algebra, which is a set representing the possible propositions which can be constructed by logical operations on the atomic propositions in the sample space. So for example, if our sample space involved the atomic propositions or events, heads or tails, we now get an algebra of propositions or events. The null event, that nothing occurred, the set containing H, which corresponds to the event that H occurred, the set containing T, which corresponds to the event or proposition that the coin came up tails, and the set containing H and T, which corresponds to either the tautology that either heads or tails occurred, right, and its corresponding event, which is just, you might notice, the sample space. Finally, our third object is a probability measure, which is a function that maps propositions in the algebra, and all those possible propositions or events, to real numbers on the unit interval. You can imagine here, For example, if we have that this is a fair coin, we might map the empty set to 0 because we don't think that nothing will happen. Indeed, we'll see later that necessarily the empty set must get probability 0. Heads to 0.5 or a half chance. Tails to 0.5 or a half chance. And heads or tails, the last element of our algebra, to 1 or certainty. We can also notice different measure spaces for different learning situations. If we think of the learning situation being one in which we're considering outcomes of the roll of a die, then the sample space, or the possible set of outcomes, will simply be 1, 2, 3, 4, 5, or 6. And the algebra, right, will give us the set of all possible events or composite propositions that we can entertain when considering the sample space. So again, the event that nothing happens, the event that the die comes up 1 through 6, the event that the die came up either 1 or 2 or 3 or 4 and so on, the event that the die came up even or odd, all the way over to the tautological proposition, the event came up something, the die came up some number, 1 through 6. And if this is a situation where we think that this is a fair die, our probability measure, P, will then map things like the die coming up any one number to 1/6, or the die coming up even or odd to 1/2, or the die coming up anything at all to 1. Now we turn to the Kolmogorov Axioms, which provide us our foundational rules for the theory of probability. The first axiom is that for any proposition, or equivalently event E, the probability of that proposition is non-negative. For example, the probability of the event that the coin toss comes up heads cannot be negative 0.5 or negative 0.4 or indeed negative anything. Our second axiom is unitarity, which states that the probability of the sample space, which, recall, represents that something happens and is equivalent to the tautology, is equal to 1. Note, similarly for the empty set, it represents nothing happens and is equivalent to the contradiction. For a final axiom, we have finite additivity. If two events are mutually exclusive, then the probability of their disjunction is equal to the sum of their individual probabilities. For example, if the probability of heads is 0.6 and the probability of tails is 0.4, then the probability of heads or tails is equal to the probability of heads plus the probability of tails, which is 1 and cannot be any other value. It must be their sum. Recognizing that here, heads and tails are indeed mutually exclusive events. When one occurs, the other cannot also occur. Good. So we have in hand now the axioms for probability theory. These three simple postulates provide us with the rest of the machinery that we employ for our most effective inductive logic. Let's move on then to lay out some simple propositions, some implications of those axioms, and a few further definitions that we'll want to use in the future. Returning to our Venn diagrams, we can give a visual interpretation of probability in terms of these diagrams. Here, we can think of the probability of any event or proposition as its area in the sample space. So you can think of the probability of the event or proposition E as equal to its area over the area of the sample space. And you can begin to think of examples where if we had equally likely outcomes of heads and tails, then the sample space would be split in half, one half being heads, one half being tails. And if I took the area of either heads or tails and divided it by the area of the sample space, whatever that was, I would get one half. And if I had a biased coin, so heads was a third of the area of the sample space, that would give me a probability of 1/3. And we can indeed extend that to rolls of a die or outcomes of a scientific experiment, and the analogy will continue. You can think of the probability of an event as the fraction of the sample space that its area composes. One useful proposition that we'll want to use is that of normality, which roughly means that every probability lies on the interval from 0 to 1. And thinking of the connection with the fraction of area notion of probability, this should make sense. The smallest fraction you can compose of a whole is 0, and the largest fraction you can compose of a whole is 1. The negation rule states that the probability of the negation of an event is equal to 1 minus the probability of the event. And you can see how this follows rather straightforwardly from the fact that the probability of anything happening at all, the probability of the sample space or the tautology, is equal to 1. And so if we want to get the probability of the negation of an event, the complementary space in the sample space with respect to that event, we know that it will be 1, which is the area of the entire sample space, minus the area of that event, the probability of that event. The implication rule is simply that when one proposition implies another, so A implies B, means the probability of A is at most as large as the probability of B. And you can think through the logic of this. If A implies B, that means that any time that A is true, B is also true. And that means that A is contained in B. Anytime we find ourselves in A, we also find ourselves in B. And therefore, the area of A can be at most as large as the area of B. Thus, the probability of A is at most as large as the probability of B. And finally, we have the disjunction rule, which states that the probability of a disjunction, so the probability of A or B, more generally than what is given in countable additivity, because you'll notice there we're also reasoning about the probability of the disjunction of events when they're mutually exclusive. The disjunction rule gives us the probability of the disjunction of events whether they're mutually exclusive or not. That probability is equal to the sum of the probabilities of the individual events minus the probability of the conjunction of those events. And you can see from the Venn diagram why that would be so. If A and B are mutually exclusive, that means that A can never occur when B is occurring. They cannot occur at the same time. And so they would have no overlap in their areas. But in general, there might well be overlap between events. And when there is such overlap between events, taking the area of one and adding to it the area of the other we'll double count the intersection of those events. So to correct for that, we need to subtract that intersection. That is, we need to subtract the probability of A and B from that sum. And notice that in the case where there is no intersection, when the events are mutually exclusive, A and B does not exist, and so corresponds to the empty set. And so it gets probability 0. So we get back the probability of A or B when A and B are mutually exclusive is just equal to the probability of A plus the probability of B minus 0. That is, we get back countable additivity as we've defined it. Of the propositions we've looked at, the disjunction rule is more challenging than the others to prove. So we're going to walk through the proof of it together step by step in order to show how this sort of a proposition can be rigorously demonstrated using the axioms of probability theory. First, note the following equivalence, that A or B is logically equivalent to A and not B, or A and B, or not A and B, as you can see from the Venn diagram, in which each portion corresponds to one mutually exclusive piece of the two propositions, A and B. From this, we know that the probability of A or B must be equal to the probability of this logically equivalent proposition, since the area they describe is the same. Next, observe that the three components are mutually exclusive, in that none is true while the others is true. Thus, by axiom 3, additivity, we get that the probability of A or B is equal to the sum of the probability of the disjunction that we derived. Now notice that A is logically equivalent to A and B, or A and not B. And B is logically equivalent to A and B, or not A and B. So again, by axiom 3, additivity, we can unpack the probability of A into the sum of two terms, the probability of A and B, and the probability of A and not B. And the probability of B similarly into two terms, the probability of A and B, and the probability of not A and B. Recall that we found the following fact, the unpacking of the probability of A or B into the sum of the three probabilities of these mutually exclusive propositions. So now we will simply add and subtract the probability of A and B, which is the same as adding 0. This is a nice little trick, and will allow us to get our expression in terms of the probability of A and the probability of B, which is what we had wanted. So now we have the probability of A or B is equal to the sum of the three familiar parts, the probability of A and not B, the probability of A and B, and the probability of not A and B. Now, at the end, adding and subtracting the probability of A and B. Notice that the probability of A and not B plus the probability of A and B is just the probability of A. That's the portion of A that does not contain B and the portion of A that does contain B being added together. Similarly, for the probability of B, we're adding the areas of the portion of B that does not contain A with the portion of B that does contain A, producing the simplified expression, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And that is the end of the proof. Now let's go over 3 definitions that you're going to find useful moving forward. Two propositions, if we remember, are mutually exclusive, just in case they are logically incompatible, meaning that their conjunction is a contradiction. From this, it follows that if two events are mutually exclusive, then their probability of their conjunction is equal to 0. And we can see this in our Venn diagram. When two events are mutually exclusive, they cannot both be simultaneously true. So we cannot be in A at the same time as we are in B. Their intersection, then, is the empty set. And the probability of the empty set has an area of 0, a probability of 0. For example, consider the events of a coin coming up heads, A, and the coin coming up tails, B, or a die coming up 1 and 6. These are mutually exclusive events. Independence. Two events A and B are independent if the probability of their conjunction is equal to the product of their probabilities. Equivalently, A and B are independent if the probability of A conditional on B reduces merely to the probability of A. For the second formulation, we can read it as saying that B being true doesn't change the probability of A being true. For example, learning that a fair coin came up heads on the first toss doesn't change the probability that it will come up heads on a different toss. The probability of heads for a fair coin on one toss is independent of the probability of heads for that coin on another toss. We can also visualize this in terms of Venn diagrams. But now we want really to create separate sample spaces for each event. Notice here we have the sample spaces omega 1, and you can think of this perhaps as the first coin toss, or the first roll of a die, or the first what have you, and omega 2, which corresponds to the second coin toss, or second roll of a die, or second independent event. And that's key. Independence means that learning an event doesn't change the probability of another. And so what that would require basically is that these exist in different sample spaces that don't interact with one another, that don't change one another's properties. Note that mutually exclusive events are not independent. Indeed, they are highly dependent. When we learn that a coin comes up heads, that is mutually exclusive with it coming up tails. But it absolutely changes the probability of coming up tails when we learn it came up heads, right? The moment we learn the coin is heads, we learn that the probability of it being tails is 0. That is really very dramatically different than probabilistic independence, which is about a relationship in which learning one event does not change the probability of the other event. Right. Independence, to have the picture in our mind, is a coin flip is independent from another when learning the result of one doesn't change the probability of the other. Heads on the first flip doesn't affect heads on the second flip. Mutually exclusive would be an event that can't happen at the same time. So on the same flip, heads and tails are mutually exclusive events. Great. Our final definition is of a deeply important concept, conditional probability. Here, we will define conditional probability as follows. The probability of A conditional on B, which we denote with the vertical bar, is equal to the probability of A and B over the probability of B. To think of how to interpret the probability of A conditional on B, think of it as the proposition, the probability of A given that B is true, or given that we have learned B. Looking at it again in terms of Venn diagrams, we can recognize that A and B is the event at the intersection of A and B, and see that the probability of A given B is going to be determined by learning that we are in B. That is, by learning that we're nowhere else. We're not in A and not B, or somewhere else in the sample space. We have learned that B is true, so we limit our focus to the worlds in which B is true. And then ask the question, given that B is true, how often is A also true? And that will be given by the ratio of the area of A and B, in particular A and B, over the area of all of B. That should make the expression of conditional probability clear in terms of these intuitions of the geometric sort. Recall that the probability of an event E was the area of E over the area of the sample space. What we see now, similarly, is that the probability of A given B is equal to the area of A and B, now not over the area of the sample space, but over the area of B. We've covered a lot of ground in this lecture, but what we want to walk away with is a familiarity with the axioms, the Kolmogorov axioms of probability theory. The ability to reason about propositions using Venn diagrams, the definitions of mutually exclusive events, probabilistic independence, and conditional probability, and the ability to begin applying some simple propositions of probability theory to solving problems. Thank you so much for joining me, and I look forward to seeing you again next time.